Last class we saw complex variables and the analytic function. Today we can see in this part the properties of an analytic function. We saw that whenever a function satisfies the CR equations, then it is a sufficient necessary condition to be an analytic. So properties of an analytic function. F of z is analytic. The real and imaginary parts f of z, u of x comma y and I into v of x comma y satisfies the Laplace equation. What is the Laplace equation? Del square u is equal to 0 and del square v is equal to 0. What is del square u? Dou square u by dou x square plus dou square v by dou y square is equal to 0. Dou square v by dou x square plus dou square v by dou y square is equal to 0. We know that a function is analytic. It satisfies CR equation. What is CR equation? Dou u by dou x is equal to dou v by dou y. Ux is equal to vy and uy is equal to minus vx. So differentiating with respect to x, dou square v by dou x square is equal to dou square v by dou x dou y. Similarly, when dou u by dou y, when differentiating with respect to y, we have dou square u by dou y square is equal to minus dou v by dou square v by dou x dou y. So adding both these things, we have dou square v by dou x square plus dou square v by dou y square is equal to 0. Similarly, we can prove that dou square v by dou y square x square plus dou square v by dou y square is equal to 0. Right? So whenever a function is analytic, we can say that the function is satisfying the Laplace equation. But the vice versa is not true. Whenever a function satisfies the Laplace equation, we cannot say or prove that the function is analytic. So the CR equations is a necessary condition and it is not a sufficient condition. The sufficient condition for a function to be analytic is that it should be continuous at the neighborhood points and the partial derivatives should exist. So we can see the next property. So w is equal to u of x comma y plus I into v of x comma y. This u of x comma y and v of x comma y both represent the real and imaginary part. When we say that u of x comma y is equal to c1 some curve and v of x comma y is c1 c2 some curve, they cut orthogonally if and only if the function is analytic. C1 c2 may vary, right? So it will be in the form of a right? It will be in like this. It will be cutting orthogonally. So u of x comma y is equal to c1, which is we are assuming that some curve. So u of x comma y is equal to some c1 and v of x comma y is equal to c2. We differentiate with respect to x. Du is equal to 0 since it is a constant. When the total derivative, du is equal to dou u by dou x dx plus dou u by dou y dy, and we find the slope. So whenever we want to prove a function or a curve or to be orthogonally, it is enough to prove that it is product of the slopes is minus 1. So we are finding the slope. Here slope of curve 1. Slope of curve 1 dy by dx, it is given as dou u by dou x divided by dou u by dou y. Similarly, v of x comma y is equal to c2, dv is equal to 0. We differentiate, we find dv. So dou v by dou x into dx is equal to minus dou v by dou y dy and dy by dx, which is equal to minus dou v by dou x and divided by dou v by dou y. So we are finding the product of the slopes. We are finding the product of the slopes, right? So ux divided by uy. So here it is ux divided by uy minus. Okay. Here it is vx divided by vy. So applying the CR equation, since the function is analytic, we have assumed the function is analytic. Applying the CR equations, we have ux divided by uy into Vx is equal to minus uy. We have the CR equations here. Vx is equal to uy, and applying this, finding the product, we get it is equal to minus 1. So product of the slopes is equal to minus 1. Therefore, the curves C1 and C2 cut orthogonally. So the real and imaginary parts cut orthogonally, which is the another property of complex variables, analytic function. So these two are the major properties where a function is analytic, then it satisfies the Laplace equation and the curves cut orthogonally. Thank you. So now we can solve one problem related to the property of analytic function. So given W is equal to phi plus I psi, which represents a complex potential electric field, complex potential of an electric field, where psi is given as 3x square y minus y cube. Find the potential function. So we have to find the potential function given the psi. First of all, we shall prove the function is harmonic. Psi is equal to 3x square y minus y cube. Differentiating once, we get 6xy, and differentiating twice, we get 6y. And again, differentiating with respect to y, we get 3x square minus 3y square, and differentiating again, we get minus 6y. And both these results, dou square v by dou x square plus dou square v by dou y square is equal to 0. So the function is analytic, it satisfies the Laplace equation. So this is a harmonic function. So we have to find the conjugate harmonic. So whenever we have a real part, we have to find an imaginary part, or imaginary part or a real part. We say in an harmonic function, these two parts pair are called conjugate harmonic function. Right? So we have to find the harmonic function phi. So previously we saw what is phi. That is dou phi by dou x dx plus dou phi by dou y dy from the derivative, first derivative. So since this is an analytic function, this satisfies the CR equations. What is CR equation? Ux is equal to Vy. So Ux is dou phi by dou x is equal to dou psi by dou y. That is written here. Phi x is equal to psi y and phi y is equal to minus psi x. So applying in this integral, if you want to find the conjugate harmonic phi, which is equal to integral, in the place of dou phi by dou x, dou phi by dou y, we have dou psi by dou y dx plus dou phi by dou y. Dou phi by dou y is equal to minus dou psi by dou x. So minus dou psi by dou x into dy. So integrating with respect to x and with respect to y, we have applying the function phi y. Already we have found what is phi y. This is 3x square minus 3y square. Applied here, and phi x is equal to 6xy, which is applied here. Differentiating with respect to x, with respect to y, 3x square, 3x cube by 3 minus 3x y square, y is considered to be constant with respect to x, minus 6x y square by 2. So we divide 6 by 2, that is 3, and we divide these 2, we have x cube minus 3x y square minus 3x y square. So adding this, we have x cube minus 6x y square plus some constant. This is the potential function what we need. So the main benefit for this is the potential function. We have to find already we have found, we have proved that it is harmonic. After proving it is harmonic, you find the conjugate harmonic. The conjugate harmonic is this one, x cube. So alternatively, we can write the function w is equal to phi x cube minus 6xy square plus I into 3x square y minus y cube. So this is the complex function. So we can find the function by using another method, which is going to be dealt in the next class, that is Milne method. We shall see in the next class. Thank you.